Hello, everyone. Welcome to Alltop School Classroom. Today, we're going to go over question number 13 in 2022, Aime 1. This is the problem. Let S be the set of all rational numbers that can be expressed as the repeating decimal in the form 0.abcd repeating, where at least one of the digits A, B, C, or D is non-zero. Let n be the number of distinct numerators obtained when numbers in S are written as fractions in lowest terms. For example, both 4 and 410 are counted among the distinct numerators for the numbers in S because 0.3636 bar is the same as 4 over 11 after you simplify. And 0.1230 is the same as the fraction after you simplify as 410 over 3,330. So find the remainder when n is divided by 1,000. Okay, notice that this said the fractions in lowest terms. That means the fraction is reduced. There's none of the fraction with the common factor between the numerator and the denominator. Before we talk about the solution, we're going to give this one concepts and theorem first. So how to find the number of positive integer which is relative prime to and also less than a given integer n. So the n can be prime factorized into prime numbers like p1 some power, p2 some power, p3 some power. And what's the answer to this question? Very easy to prove, but today I just give you the result. Such a result should be like this. Each of the power of prime, and then you just minus the one less than the power of that prime number. If this one already one, that actually is just a p1 to the 0 power, which is 1. So you just multiply these together, you get the count for those integers, which is relative prime and also less than this integer n. So we just give example, n equal to 720. 720, you certainly can factor into 2 to the 4th, 3 squared times 5. Yeah, basically from 8 times 9 times 10, you get a prime factorization, 2 to the 4th, 3 squared, and then 5. And then how many number relative prime to 720 and also less than 720? Based on this one, we will get 2 to the 4th minus 2 to the 3rd, 1 power reduced. And then multiply by 3 squared minus 3 to the 1st power, 5 to the 1st power minus 5 to the 0 power, which is 1. So such a number, such a count is 8 times 6 times 4, which is 192. So that means we can find out 192 numbers are relatively prime and also less than 720 based on this basic formula. Okay, that's an important statement, theorem, over here before we explain the problem. Okay, let's start working on the problem. So the repeating decimal with a 4-digit repeating, we can write this as the 4-digit number over 9,999. Certainly, ABCD is not the one we're going to count how many 4-digit number, because these numbers maybe can have common factor with the 9,999. So we just count those numerators which qualify for the reduced fraction, not this original fraction. So we have to take that into consideration. So let's just factorize this denominator 9,999 first, which is 3 squared times 11 times 101. Very easily to do the factoring. So once we get this one, we can consider the numerator in several cases. The first case will be the numerator is relatively prime to the whole denominator. That means it's already been reduced. We don't need to find any common factors because the common factor will be 1. So that means the numerator is relatively prime to 9,999, certainly less than this number. So denominator, you just keep this as it is. So how many such a number based on the previous theorem? We know it's easy to get the results. So certainly the fraction in the form some numerator over 9,999, or it's just some number over 3,333. Okay, that could be in this form or in this form. But anyway, that's going to be, this n will be relatively prime to 3, 11, and 101. And then definitely relative prime for the entire thing, 9,999. How many such a number? Based on the previous one, we just do 3 square minus 1 of minus 3 to the first power, 11 minus 1, 100 minus 1, you multiply them together. 9 minus 3, 6, 11 minus 1, 10, 101 minus 1, 100. So you get a 6,000 such numbers. So we get a lot of numerators with this denominator 9,999. And certainly could be in this form. Okay, and that's first case. We get the numerator relatively prime to this 9,999. We get a 6,000 of them. These numbers certainly don't include the following: multiple of 3, multiple of 11, and multiple of 101. So are these still qualify as part of the counting? Certainly, as long as the fraction is reduced, we're going to include them. If these numbers included on the numerator, so certainly denominator should not have this as a factor. For example, the entire denominator is supposed to be 3 squared times 11 times 101, but if you get the numerator is multiple of 3, so the denominator cannot have this 3 as part of it. It has to be the remaining part of the 9,999. Same thing, if the numerator is going to be multiple 11, so that means the denominator should be either definitely don't have this 11 as part of this fraction. So that should be something else like 3 squared times 101. So if the numerator doesn't include the 101, numerator is is a multiple 101. The denominator can only include the rest of it, which is 99. But this one already is larger than 99. So the third case, certainly, we won't be able to find anything. We're going to go the detail after this. So the case 2, you see the numerator is a multiple of 3s, and the denominator is the rest of it. The other factor of 9,999 not containing 3. So the fraction is in this form. 11 times 101, which is 1,111. So n is not a multiple 11 and also not a multiple 101. So that's a multiple of 3. The number of value for this one, multiple 3, will be 370. When you divide by 3, 1,110 divided by 3, because we should n will be less than 1,111. So we use 1,110 divided by 3, we get 370 such numbers. But that's really not everything. Actually, this is too much. This including those one, it's still have some of the multiple 11 in it, some of the 101 in it. So which is still multiple 3, but we should exclude those number, which is multiple 11, multiple 101, and also multiple 3. So obviously that's going to be multiple 33 or multiple 303. We just remove them. So 1110, this number, if they are multiple 33, that will be 33 numbers. Okay. And then if these are multiple 303, that will be only 3 of them. Okay. That's we exclude both of these. 33 of them should not be in this form because this number will not be reduced with this new denominator as 1111. So we just remove them from the total of number of multiple 3 from here, and then cross this out, and then we get the actual number of qualified multiple 3 as the numerator in this form. So that's a second case. But for this one, we still have some leftover for multiple 3. So because we noticed that the previous calculation, we don't include those multiple 33. And also we don't include the multiple 303, which is still multiple 3. So we need to consider that as in our counting for the numerator, but we're going to consider in a moment. Now we're going to consider the third case. N is the numerator is multiple 11. So the denominator definitely won't have the 11 as part of the factor, 9,900, because 9,999 equal to 9 times 11 times 101. You have the numerator is multiple 11, so the denominator can only have 9 times 101, which is 909. These are actually the other factor, 9,999, not a containing 11. So this is a 9,999. So on the fraction in this form, the numerator over 909. So the number value, you could just do 908 divided by 11. So that will be 82 of them. Okay. But notice that we need to remove those n which are also multiple 3 and a multiple 11, multiple 1 at the same time. Is that possible still have those numbers? Multiple 3, that means this is multiple 11 at the same time is multiple 3. That's going to be multiple 33. And if it is multiple 11 and also multiple of 101, that means this will be multiple of 1,111. But the denominator 909 is less than that. So this one, we don't need to worry. Okay. So we only consider those one is multiple 33. How many of the multiple 33? Just do 908 divided by 33. And among these 82, we have 27 of them, which are, multiple of 3 and a multiple 11 at the same time. So these one, we need to exclude them. Okay. We need to exclude this one over there. So the actual qualified numerator in this case will be only 55 of them. 82 minus 27, 55 of them. So that just the numerator is multiple 11. Okay. The next case, certainly we already noticed that we still have some leftover for multiple 3 and also multiple 11 at the same time. This time we already noticed that leftover for the multiple 11 is multiple 33 as well. The same as the leftover for multiple 3, we didn't count it. So now we're going to consider this common case, which are leftover from them. So the next one would be the case 4. The that's going to be the numerator n is going to be multiple of 33, multiple 3 and a multiple 11 at the same time. Denominator is going to be something else. For example, we get is originally you're going to get something over 9,999. Okay, but since we want the top one is something model 3 or 33 times something, so this one cannot have 9, cannot have like 3 squared. This is 11, this is going to be 101. So certainly we cannot have the 3, cannot have 11. The only possible value on the denominator will be 101. So that's why this will be 101 as the denominator. So that's why we say other factors of 9,999 not containing 33. Okay, so that's become very simple. The denominator is 101. The numerator is this n is multiple of 33. How many of them? We just do 100 divided by 33. We get a 3 value of them. So certainly this 3 value doesn't really have any invalid numbers. Okay, that's purely what we want. Okay, you cannot get like a 33, multiple 33 also at the same time is going to be multiple 101 because the that's already exclude those one out. So that's less than 100. So it won't be multiple 101. So that's case 4. The next one is, it may not be a problem, but I'm going to verify the numerator is that possible to be multiple 101? You know, 9,999 equals 3 squared times 11 times 101. The numerator is going to be 100 multiple 101. The denominator can only have something else, which is 3 squared times 11. That should not contain the factor of 101 coming from 9,999. So this is going to be a trouble because the numerator is a multiple 101, at least 101. So the denominator is 99. That's not valid because this is going to be reduced to proper fraction. So this we cannot find the integer value for this n. So the case 5 is not really a valid case. We don't have a result for this. So basically, we got the number of possible numerators completely. They're going to be the first one relative prime to 9,999 for everything. For the first one, right? And then the second one will be, the first one is 9,000 relative prime to 9,999. The second case is going to be multiple 3, but not a multiple 11 and not a multiple 101. This one is multiple 11, but not a multiple 3. But this one is going to be multiple 33. So we get complete list of those numbers for the possible value of the numerator. So the result should be 3,692. And then we find the answer. So we are done then.